Welcome to this month's edition of the Utah Forge Modeling and Simulation Community Forum. We're pleased to have Professional Mukul Sharma from UT Austin. Going to talk today about some of his fracture design work he's doing as part of his Utah Forge Solicitation 2020-1 award. So I'll turn it over to Mukul. I'll ask if you have questions, please type them in the chat. I will moderate the Q&A. If we have enough time at the end, we'll let people just speak them out, but I'll watch that and monitor it as we go. And with that, I'll turn it over to you, Mukul.
Thank you, Rob. So thank you all for joining. I think the talk today is going to be primarily on looking at designing the hydraulic fracture treatments that we plan to do in the 16A well early next year, and the models and modeling that we've done to support that. The work has been done with the help of two graduate students, Mung Kao, who just got his PhD this past month and is now at Lawrence Berkeley Labs, and Quinn John Liu, who's a PhD student here. Okay, so our primary objective is to present 6 possible fracture stage designs that could possibly be pumped in the 16A well at the Forge site. And the goal of the fracturing stages is to evaluate which completion design and which pumping schedule provides the best possible fracture characteristics under the constraints of the well that we have. Of course, what we're aiming for is the following key characteristics that are desirable for these fracs. So each fracture in a given stage should take equal amounts of water and proppant. I'm assuming there's going to be multiple clusters of perforations taking fluid and sand. We want to ensure uniform fracture propagation in all the clusters in the stage. And if possible, fractures should intersect both the well bores. So this is absolutely key if you want to be successful in circulating fluids in this geometry. And some degree of fracture complexity, branching and turning, should be achieved and should be beneficial in terms of increasing the surface area of contact between the fracture and the matrix, so that you can get heat recovery from these things. So that's what we're shooting for, what we have looked for is designs that will allow us to get to this point. So there's a bunch of design parameters that can be changed to try to achieve this. Of course, the number of perforation clusters can be varied. The number and orientation and diameter of the perforations in each cluster can be varied. Pumping rates, proppant loading, proppant ramp up, proppant size, whether to use proppant at all, sequencing of fractures in a stage, and the fracturing fluid viscosity. Use just a slick water or a viscosified fluid, or a combination of the two. So those are the various parameters that I think are key to designing a fracture treatment that would give us the maximum, that would give us the characteristics of good connectivity, good conductivity, and ultimately good heat recovery in the system. So we've explored many different frac designs, and we are suggesting some designs that I'll put before you, and would love to get your comments on it. So to get there, what we have used is our fracturing simulator, which we have been building over the last 15, 20 years. What it does is really solves the equations in the reservoir domain. So you can solve the pressure and component balance equations in the reservoir. This allows you to do multi-phase compositional simulation in the reservoir. It also solves the deformation equation and the temperature equation, so you can do heat recovery calculations in the model as well. And we've recently added a geochemical model to this as well. The next domain is the fracture domain, and this obviously is coupled to the reservoir domain, where we do the same component balance equations, proppant transport, fracture temperature, and so forth. And these are all coupled with the reservoir domain. And we have a wellbore domain where we have component balance equations and wellbore pressure and wellbore temperature in this. And one of the key things here in the wellbore is looking at proppant distribution. how the proppant is distributed across various clusters if you have multi-cluster perforating and fracturing. So I'm not going to go through any of the details of the model. It's all been published and it's available. If somebody's interested, I'm more than happy to send you more details. One of the unique things about the model is that the fractures that we create are modeled explicitly. So we are not really modeling fractures as high permeability grid blocks. We're actually modeling these fractures very explicitly, where you can calculate the displacement and the width of the fracture and the stress that arises as a result of the creation of this fracture. So interactions between the fractures and natural fractures can be properly accounted for. The way we account for the interaction between fractures, hydraulic fractures and natural fractures, is through displacement discontinuity method. We have the option of doing it using finite volume methods or displacement discontinuity. For this project, we use this displacement discontinuity methods. We also have flow inside the fractures, as I said, and you can actually solve for the pressure and the rates and so on in a fracture network. And then you can solve these implicitly or semi-implicitly in the code. The first step in this whole process, of course, is to generate a DFN, a discrete fracture network. I had given a talk on how to create these discrete fracture networks using the data that's been collected by the Forge teams, various Forge teams. So I'm not going to talk about how we created the DFN because there's a report on it, there's a paper on it, and also there's a recorded seminar that I had given about 6 months or a year ago. So we assume that we have this DFN, which is consistent with core data and log data, the 4 sets of orientations of fractures, and so forth. So all that's been incorporated into this in 3D. The direction of propagation of the fracture is also controlled by the interaction between these fractures, and I'm not going to spend any time on this. One important thing I want to mention is that the interaction of the hydraulic fracture with the natural fractures is controlled by the normal and tensile stresses at the natural fracture faces. These are all displacement discontinuities. So in other words, every natural fracture is a displacement discontinuity, and we solve for the stresses at those locations. And we use DDM to compute the normal and tensile stresses. The fracture can either slip, the hydraulic fracture can either slip along the natural fracture or can intersect it, or can kink along it. So you can go for a while along the natural fracture and then cross it. We have accounted for changes in pore pressure due to leak off. We have accounted for changes in pressure in the natural fracture. And this is published, these studies are published in the last couple of years. So this actually can have a significant effect on whether the natural fracture will slip or whether you cross it. So changes in the pressure in the natural fracture certainly is important. The last thing I want to emphasize is the fact that we do account for the distribution of sand and fluid in the various perforation clusters through what we call the proppant transport efficiency. So this is part of the wellbore model, and it accounts for the fact that you can actually get quite a bit of higher concentration of sand or proppant towards the toe side of the wellbore as a result of the inertia of the proppant particles themselves. So as the proppant particles are being moved along the wellbore, they will concentrate towards the toe of the well. So here's an example of the proppant concentration passing through the perforations. It could be quite low, 1.5 down here, but it could be much higher, around 4 towards the toe of the well. So the concentration near the toe could be quite a bit larger than what you're pumping as a result of the inertia of the proppant particles. And this has been accounted for in the simulations that you'll see. We got into this business primarily because of some fiber optic data that was being collected by Shell at the time in 2016, and the large concentration of sand towards the toe leads to screening out of some of the perforations towards the toe, and this screening out is observed in these fiber optic data, in the DAS data that you see here. So in this DAS data from 2016, you can see that basically the perforations towards the toe go quiet after some time, and you really don't see much sand going there after a certain time, after it screens out. And there are several papers that we have on this that we can certainly point you to. I'm going to spend the rest of so that's all I'm going to talk about as far as the model is concerned. I'm going to spend some time talking about the results of what we are planning on, what we propose to pump in the 16A well. So the base case that we built is a frac stage which consists of 3 clusters with a 10-meter cluster spacing or 30 feet cluster spacing, with 7 perforations in each cluster, 0-degree phasing, all perforations pointing up, and slick water as being the frac fluid being used. The pumping schedule that we have modeled and proposed is, this is the injection rate versus time, and this is the proppant concentration and size. So we are proposing 100 mesh sand in this particular treatment. With the proppant concentration slowly ramping up to about 1.75 ppa. So if you look at the results of the simulation, what you find is that the fractures do turn, but they're largely planar. So these 3 clusters, this is the top view, and you can see that the fractures do propagate up and down, and they're largely planar. The 2 wellbores that you see here are the 16A and the 16B wells. And the one thing that you notice is that one of the fractures goes up and intersects the 16B well, which is what you want, while the other 2 fractures tend to migrate away from this fracture and away from the 16B well. So out of the 3 fractures that you're pumping, only one of them is actually intersecting the 16B well. This is entirely a result of the stress shadow that's being created by the growth of these fractures. And so the growth of these fractures results in them interfering with each other. And if you want to visualize this a little bit better, you might see it's slightly better here with the 3 clusters here, 1 fracture going up and intersecting it, the other 2 going off to the side, trying to avoid this fracture because of the stress shadow that's being created by that fracture. I do have a video of this, which might allow you to visualize this better than okay, that didn't do any good. Escape. So, oh, there it is. It's down here. So you can see as we rotate this, you can see how the fractures are growing. And one of the fractures intersects the 16B well, while the other 2 tend to take off and go off to the side and don't quite make it to the 16B well because of the stress shadow effects. This is something that we expected in terms of the fractures going away from each other because of stress shadow effects. And so we want to avoid this kind of a situation because we want all 3 fractures to intersect the 16B well. This may be achievable by changing the spacing between the fractures and doing some other things. So, but it gives you a reasonably clear picture of how these fractures are growing and how they might interfere with each other in the process of overcoming the stress shadow and then growing away from each other as a result of that. We also have created the microseismic cloud that the simulator would predict based on the creation of these fractures. And this microseismic cloud is what we would like to be able to match with the measured microseismic data that we will collect as a part of the fracturing, as a part of the stimulation treatment in the 16A well. You can see the time evolution of this microseismic cloud from the simulations, which we hope to compare with the data that will be collected down the road as we stimulate this well early next year. So again, this is just a way of doing narrowing down the diagnostic possibilities of the fracture geometry in this. We also have the surface treating pressure in this in the well, and this is something that we have modeled with the model, and you can see that the limit was about 8,000 psi. We've gone above that in this particular design, so we can certainly change that to accommodate this design. I want to contrast this frac design with another one that I'll call the Texas two-step design, which actually is very hard to implement in this well, but you can implement these in wells that have sliding sleeves. And what you are doing here is you create the fractures one at a time. So you create one fracture, then you go towards the heel and create the next one, and then you come back in the middle and create the third one. So number of clusters is still the same. Number of perforations per cluster is the same. The cluster spacing is the same. Phasing is the same, etc. Now each cluster is fractured individually in this sequence 1, 3, 2. So you frac 1, frac 3, and then come back and do frac 2. So that's the idea here, and you can see that this time the fractures tend to be a lot more planar and a lot more going off in a similar direction in all these cases. And if you play the movie here, all three fractures do intersect. So you create one fracture that intersects the 16B well, then you create the second fracture, and then you create the middle fracture. And so this fracture is being further away from the first fracture, does migrate up as well into the 16B well. And then the middle fracture has a stress shadow on both sides of it. And because of the stress shadow on both sides of it, it actually also tends to propagate up as well and intersect the wellbore. So you get good connectivity between the two wells when you use this particular strategy, which we can implement in the 16A well, but it would be hard to implement in the 16A well without any sliding sleeves. So this is something that we would definitely recommend if it's possible, but would be difficult to do in practice in this particular well. But it does offer some clear advantages to the way that the two wells, the fractures would be connected by the fractures would connect the two wells. We've also generated the microseismic events in this particular case. And you can see the microseismic events being generated for each of the fractures being created one at a time, basically. And so we would like very much to be able to see what this looks like in the field, if this is pumped at all. Right, so this is, excuse me. I'm sorry, I'm a little hoarse today because I'm a little bit under the weather, so apologize for my coughing in. The surface treating pressure is seen here. The pumping rates are obviously lower. They're 1/3 of what the pumping rates were in the previous stage, in the previous example, where all three fractures were being pumped at the same time. We also explored the possibility of doing tapered completion designs with 6, 7, 8 perforations per cluster. Again, everything else is exactly the same, except you now have more perforations towards the toe and less towards the heel. We've done many cases like this. We've done 5, 7, 9, and so on. So various combinations of these, and you can see that the geometry of the fractures is indeed different. You tend to get fractures that do have a better chance of intersecting the other wellbore, but you still get only one, or in some cases 2 fractures intersecting the second wellbore. So this connectivity between the wellbores becomes a central issue for us in terms of the frac design, so that we can get pretty good connectivity between the two. Now, I will say that the results of this model of these models depend very much on how much slip there is at the natural fracture and how easily and how much they slip. The microseismic data that we had calibrated our model to seems to suggest that we have done an adequate job of calculating that slip, because the magnitude of the microseismic events is comparable in the measurements as well as in the simulations. But if you have more slip and more relaxation of stresses, you may see less stress interference effects than we compute in the models. So you can also see how these fractures propagate in 3D. By the way, these effects that we are observing here are only observable in the models that are run in 3D. If you run the same model in 2D, you will not see these effects, because obviously these fractures are moving away from each other in 3 dimensions, not in 2 dimensions. So it's important to run these models in 3D and not in 2D. But you can see how these fractures tend to avoid each other as you go. So we do have microseismic events generated for this case as well, and the treating pressures as well. We also ran a case with exactly the same parameters as the base case, but with no propant at all. And the idea here is, well, if the granite is very impermeable, and if you create these fractures, maybe the roughness on the surface of these fractures is sufficient to keep the fractures propped open. Now, this doesn't seem to be the case in the stages that have already been pumped without propant. They seem to have poor conductivity, and so circulating fluid between the 16A and the 16B wells has not been as easy as we had hoped. So this may not be a treatment that we actually pump, but we thought it would be interesting just to compare and see how a fracture with no propant would behave, and what kind of results you might get with this. So it's open to discussion as to whether we'll actually pump a treatment that has no propant, because we already done it with one cluster, with one set of perforations, and that hasn't given us enough conductivity to circulate fluids effectively. Again, the geometry of the fractures does change as a result of this. You do get some limited amount of turning and branching, but in these cases as well, you get 1 or 2 fractures that intersect the wellbore, depending on precisely how you pump the treatment. So you can see one of the fractures intersecting the wellbore pretty readily, and then the other 2 trying to get there, and then the second one intersect. In this particular case, the second one intersects the wellbore as well. And so you do get, this is quite sensitive to what the rates are and what the ramp up of the rates is, and so forth, right? So this is something that we have found. We've also generated microseismic events for this, which I will skip over for now, and the treating pressures. We also tried a viscous frac fluid. So this frac fluid has a viscosity of 10 centipoise. So this is a high concentration of polyacrylamide. So you basically up the concentration of the friction reducer, and everything else being the same. Again, you see fractures that turn a little bit, but not a whole lot, largely planar. And you do see fractures that actually are migrating away from each other, even more so than before. And so you do get one of the fractures intersecting the wellbore, clearly intersecting the wellbore, and the other 2 are marginal. They are unlikely to intersect the fracture, the wellbore, with this more viscous fluid, and the microseismic events for this stage as well. This is the treating pressure for this particular treatment. We also tried a case with 6 perforation clusters, where you have 6 perforations in each cluster. So 666. And the pumping schedule had a higher rate. And so you're ramping up the rate to a higher value. And what you end up with is fractures that look like this, where you have a couple of these intersecting the 16B well, and the other fractures going off to the side to try to avoid the stress shadow created by these fractures. I can show you a movie of this one with the 6 fractures growing. It's a little bit hard to see because it's in 3D, and it's kind of tough to visualize this. But you see 2 fractures intersecting out of the 6 intersecting the 16B well, and of course the other fractures are veering off to the side and causing, because of the stress shadow effects. But 2 fractures certainly intersect this. The third one comes close, but not quite there. And so this is something that would be interesting to pump. There's some debate whether we should be pumping 6 clusters in a stage or not, because the connectivity is going to be affected by this. So you can see the first one intersecting, the second one intersecting 16B well. And you do see the net pressure in this case as well. We also have run some cases to try to vary the cluster spacing, 10 meters, 30 meters, 20 meters, 30 meters. And you do get more likelihood of fractures intersecting the 16B well when you have a larger spacing. The only problem, so for example, for 30 meters, you clearly see these 2 fractures because the stress shadow is less significant at larger spacing. You see 2 of the fractures intersecting. The third one doesn't quite intersect the 16B well. So you do get more intersections, but of course, with 30-meter spacing, you get fewer fractures overall connecting the 2 well bores because you have fewer, the spacing between the clusters is more. So this doesn't really solve the problem. In fact, it might make it worse because you have 2 intersections over 30-meter spacing between the clusters. So over 60 meters, you're getting these 2 intersections. So this is, we've looked at these as the different possible cases. And what I want to do is to summarize so I leave enough time for questions and discussion. So perforation cluster design has some influence on fracture geometry and the distribution of proppant and fluid in each fracture. You can redistribute fluid and proppant more efficiently by varying the number of perforations in each cluster. The large number of perforations will result in very non-uniform fractures. So limited entry perforation designs are absolutely a must in most of these cases. So having a large delta P in the perforations is essential. For the low concentrations of proppant that are planned to be pumped, it is not essential to taper the perforation clusters. Having the same number of perforations in each cluster is okay. The simultaneous pumping of all fractures results in only 1 or 2 out of the 3 fractures intersecting the 16B well, which is about 100 meters above the 16A well. The limited fracture height growth in these fractures is due to the stress shadow of the adjacent fractures, which force 1 or more of the fractures to grow longer rather than taller. So it goes off to the side rather than up into the 16B well. The natural fractures that we have put in, that is the DFN that we've created with the log and core data and microseismic data calibration that we've done, does not result in wholesale turning of the fractures. This you do get some turning, you do get some deviation of the fractures in the direction of the natural fractures, but not a large amount of turning. And in fact, you do get some degree of branching as well. This is largely a result of the hydraulic fracture being much larger than the natural fractures in the DFN, which is something that we confirmed in our earlier work on matching the microseismic data. So we did try to use longer natural fractures and shorter natural fractures, but the best matches we got with microseismic data was with this particular size of natural fractures that I showed you the results for. And as a result of those sizes being smaller than the large hydraulic fracture, you tend not get as much turning. Also, the stress contrast here is reasonably high, and so you do tend to get more planar fractures as a consequence of that. So increasing the cluster spacing from 10 meters or 20 or 30 meters results in less stress interference, but there is still insufficient height growth to allow all three fractures to connect both the wells. Injecting more volume of fluid does not resolve this issue. So we tried larger volumes of fluid being injected. Injecting at a higher pumping rate makes the situation worse. So that's not something we would recommend. So the injection rate should be high enough to ensure that you get limited entry designs, so you get more uniform propagation of fractures. But this business of stress shadow and fractures not intersecting the well above is something that is not resolved by higher pumping rates. The Texas two-step or the alternate fracturing sequence 132 is found to allow all the fractures to intersect the 16 B well, and this can substantially improve the geothermal heat recovery rate for this well pair. Unfortunately, it's not so easy to do this particular sequence of fracturing without using sliding sleeves. So it's possible, but it's not easy to do. So it's something we need to debate as to whether it's worth going through the trouble of doing the Texas two-step or the alternate fracturing sequence in this particular design. It does help, though. It certainly helps in better connectivity between the wells. So the completion design, the design of how you frack the wells, is going to have a large impact on the connectivity and the conductivity of these fractures that connect these two wells. So it's an extremely important part of what we would like to discuss and talk about as to how we should design these fractures. And the ability to model these fractures and the growing fractures in a DFN is something that has allowed us to study this problem in much more detail than had been possible in the past. So we do have some additional results for various different cases, which I'm not going to talk about today, but I'm going to stop here and see if you have any comments, suggestions, questions. Be happy to entertain those. Thank you.
Well, thanks, Mukul. Great presentation. I really enjoyed it. I have my own questions, but I'm going to hold mine till last because I know I can get a hold of you pretty easily. We have a number of attendees that submitted some questions. I'll go through them and read them. Mark, I see your hand up. I'm going to hold you off till I go through the questions that are in the chat.
Sounds good. Thanks.
Okay. So Leopoldo Sierra asked two questions, and I'm just going to go through them and I'll combine them to some degree. And the first one is, based on what you're showing, do you think that it could be better to use one cluster to have a better chance to intersect the wellbore?
That is correct. Yes. Using one cluster is certainly the way to get to the highest probability of intersecting the wellbore above. The problem with doing that, of course, is we would like to be able to make this fracturing process more efficient. And so we would need multiple clusters ultimately in commercial wells to be able to do that.
Okay. I was going to follow up with that question of why. He also followed up with, additionally, your modeling is showing mostly planar fractures. If this is the case, what is the benefit of considering natural fractures to set up the model?
Well, I think we did not know a priori that the natural fractures, how much deviation from planarity you would get with the natural fractures. We just didn't know that. In fact, if you change the parameters in the natural fractures in terms of all the stresses, the stress contrast and the size of the natural fractures, you are going to get lots of branching and lots of complex fracture networks. Whether we actually get this sort of planarity is something that we are going to discover once we collect the data, right? The best we can tell right now with the data we have is that we get largely planar fractures. You notice that the fractures weren't quite orthogonal to the wellbore. They were deviating towards the orientation of the natural fractures, and we were getting some limited degree of branching. Now, the model input parameters may be incorrect, and if that's the case, then you will see more branching. When we run tracer tests and we run fiber optic diagnostics on these wells, we will know how many intersections we get. That's the good news, is that the fiber will actually be able to tell us how many intersections we're actually getting. You know, are we getting 1 or 2 or 3 or 4 or more? So we will know the answer once we do the stimulation and we measure all the fiber.
So I'm going to challenge you a little bit on that one, Cool. So, I agree with you 100%. I'm really happy to see we have fiber downhole now, so we can get some distributed sensing on some of this. But in the first 3 stages that have already been completed in 16A, the lower 2, stage 1 and 2, did use a slick water, and the microseismic we observed in those, while the catalog I would say is incomplete due to some monitoring challenges, it did seem to be a lot more diffuse. I would say it didn't seem like we didn't really be able to pull out 1 or 2 large planar features from those 2. The third stage, when I used a viscosified fluid, I think it was, we did get a lot more planar response. Can you comment on that?
Yeah, I think what I'm talking about here is primarily the backbone fractures, the fractures that actually conduct fluid from one well to the other. You are going to get some branching and some microseismic events that occur outside the domain of the main backbone fracture. So these are isolated fractures or dead end fractures that don't really contribute very much to the geothermal heat recovery. But you're right. The microseismic events in stage 1, for example, clearly showed that there was a cloud of microseismic events. Most of those were not part of the backbone fracture that would connect the 2 wells.
That could very well be the case. I do think that when we were doing some of the flow testing, we were putting a lot of fluid into storage in that reservoir. And we didn't necessarily see coming out, but there's other challenges there that we'll have to deal with that. So I'm going to move on to the next question here. And those of you that are typing questions now, you can just raise your hand. Since Mukul is done speaking, I'll just call on you and let you ask your questions in order that I get them. But I'm going to come back here. Luke Frash, he had asked about what's limiting the downward growth. Is there a stress barrier or a contrast in the fluid pressure gradient or lithostatic stress gradient?
Yeah, that's a good question, Luke. So we do get some downward fracture growth, but it's because of the stress gradient in the formation. Most of the fracture growth is above. You do get some amount of fracture growth down there, but the stresses are clearly much higher as you go further down, and so that is something that has limited the downward growth of the fracture.
Okay. Bo Lu, I see your question there. I'm going to let you ask it. It seems a little bit, I think there's some vagaries in how you phrase your question. So I think it may be better, instead of me trying to interpret what you're asking, if you ask it yourself. If you want to come off mute, please do and ask your question.
Okay, thank you, Robert. So Professor Sharma, so my question is, how can you recognize the seismic events during your simulation?
Could you repeat that one more time, please?
So my question is, how can you recognize your seismic events during the simulation?
How do we create the microseismic events in the simulations? Is that what you asked?
Yeah, yes.
Okay. Yeah. So we actually compute where you have dilation and shear failure events, and wherever these events are, the magnitude of the slip of the displacement of those events allows us to compute the moment magnitude, and the orientation of those events allows us to calculate the moment tensor. So it just depends on what the displacement is at any particular displacement discontinuity. And if there is displacement there, then it'll generate a microseismic event and we can compute that.
Okay, got you. Thank you.
Mm-hmm.
Thank you. And Mark, you want to come off and ask your question?
Yeah, so I guess it's more of a comment, but Mukul, I'm interested for your comment on my comment or just a discussion. Yeah, so I've done some similar kind of modeling. Last January at Stanford Geothermal Workshop, I had a paper where I matched stage 3 with a planar frac model. had to vary some things like the fracture conductivity during propagation, and got a really nice match of the geometry. So more recently, we've taken some kind of standard out of the box frac designs, 8 clusters per stage, pumped a normal slick water frac job in them. And you'd probably see about 7 out of 8 intersect a well above 300 feet above. I think we're getting a little different results because I think I have more viscous pressure drop. And so by no means are the fractures all the same, but they are certainly going in different directions. And if you put a well to the right, you would not see 90%. But at least when I've done this similar type of modeling, I saw more frac hits up above. And I just think it highlights maybe the non-uniqueness of this question. And like you said, ultimately we'll get better data like from the fiber, and that'll allow us to maybe constrain some of that. But I just wanted to comment. I think there's some uncertainty there.
That's interesting. So how many clusters did you have in your simulations?
I think about 8 in a stage, and
8, okay.
good limited entry completion. And again, the fractures are not circular. They kind of go off in different directions. But part of my calibration was to have more viscous pressure drop. Kind of capturing that it's kind of planar, but it's not really perfectly planar. So the cubic law is not actually perfect.
And the viscous pressure drop was higher because your fluid viscosity was higher, or was it just lower width? Or
no, well, so a standard thing we do in our modeling is we don't quite use the cubic law. So it's pretty common to say,
I see.
Like if you look at the core, in either shale or recently in forage, they don't actually see one planar fracture. They actually do see a swarm of planar fractures. And so if you're distributing the flow across more fractures, or the fractures are more irregular or branched or something, then it's not just a flow through a slot anymore. And that could create additional viscous pressure drop. And so what we do is we literally just take the aperture, we multiply it by a factor, like just multiply it by 0.5, and then we put it in the cubic law. So you made the conductivity during propagation 8 times lower. And if you do something like that, you get, less irregular shapes, still irregular, but less irregular. And that's, it was actually, I had to do that as part of the match to the stage 3 geometry.
That makes sense. In other words, if you were to reduce the slot width by a factor of 2, let's say, which is what you said you did, then of course you'd get much larger pressure drop, viscous pressure drops in fracture, and that would give you more intersections and less. The impact of the stress shadow would be reduced as a result of that, for sure.
Yeah,
so that
yeah.
makes sense. How do you and how do you justify that? I mean, how do you say that that's a reasonable thing to do? We haven't done that, so I'm just curious how. I mean, we can do it quite easily, but I'm just
right. You could, yeah, it's simple. Well, I mean, there's 2 reasons. One, because it helps me match data a lot better. So this is pretty limited EGS data, but having done a gajillion projects with fiber and shale, it often is helpful.
Okay.
And then the other is, again, I mean, when I look at core, I don't see one perfect parallel plate per.
So the roughness of the fractures is what you're trying to account for.
The roughness, and perhaps the fact that it's not just one crack. I mean, even though I'm calling it one crack, it's a planar crack model. I don't actually think it's one crack.
Yeah.
And so maybe, in fact, Pingjing Fu and the guys at Lawrence Livermore had a nice paper a few years ago where they worked out some of that math, and they said, yeah, if we call it one crack, but it's really 5 cracks, then the conductivity is actually quite a bit lower than we think it is. Yeah. And that would also affect leak off. And in fact, in my model, I had leak off substantially elevated. I made the effective leak off 100 microdarcy. That was the effective permeability. So, more leak off, more viscous pressure drop, and more toughness, all of those things would arise from multiple strands. So yeah, I'm hand waving. Yes.
That's real interesting. I mean, we should try some of those things. We should definitely, we have not done that. We've basically assumed a planar slot, and we've assumed a single fracture. So we should definitely try some of those things and see what happens.
Yeah, it's worth playing around with.
Well, it would be interesting also to get comments on what you think of what kind of frac designs we should try out in the next 5 or 6 stages. That would be a really interesting conversation to have. Maybe not now, but maybe at some point.
Happy to discuss that. Yeah, I certainly do have thoughts.
Okay.
All right, I want to move on to our next question.
Right.
Alita, do you want to come off mute and ask your question?
Hey, sure. Hi, Mukul. I was just trying to remember your DFN model. Are your natural fractures all vertical, or do you have some dip in there? And also, I kind of recall the aspect ratio being such that they were quite long compared to their height. Is that, am I remembering that correctly?
Yes, I unfortunately don't have the slides here with me for the DFN presentation, but you're right. All our fractures are vertical. They have 4 different orientations, based on your work.
Right. So you took the 4 azimuth orientations,
Correct. We did the four azimuths.
but you didn't take the dip.
We did not.
So those aren't really the same four planar features that
Correct.
we have found from the data.
Yeah, we did not have any dip in our model. You're right.
So yeah, so I'm just wondering, you know, and also the aspect ratio, aren't these like sort of very long compared to their height?
They are actually the length and the height are actually comparable. The length is, I think, 2 or 3 times the height.
Okay. All right.
So they're
I'm
not
just
like 10
wondering if
times
that would
longer.
affect.
They may be 2 or 3 times longer. And we did try different lengths of these fractures. So we did try to make them longer and shorter.
Right, but you didn't vary the width, the height of them.
We
You
did
just made
not.
them longer.
We did not
Yeah.
vary the height.
Which is again just sort of a very different shape to natural fractures than the models we've been
Would you
using.
suggest that we try to vary the height as well?
Well, I would suggest that you have the height the same as the length. So we always used an
Okay.
aspect ratio of 1 on our
Okay.
fractures because these are an igneous intrusive rocks where you're not
Okay.
expecting the heights to be limited by, say, like in sedimentary rock, by different lithologic boundaries. Although we do have some lithologic boundaries, but we don't expect them to be necessarily horizontal features. So, so yes, I guess I have a hard time getting past the geometry of your natural fractures to say that they would have so little effect on your propagating fractures, especially with a slick water treatment.
Hmm. So you think that the natural fractures should fail a lot more easily in shear, and then the hydraulic fracture would propagate along
Well,
those directions? Is that
well,
what you're thinking?
certainly allowing them to have some dip, not having them be vertical features is going to change their propensity to shear,
Uh-huh.
to fail in shear. That's going to be a
True.
big factor there. So
True.
you're not looking at that, and also the fractures we had in our models were much larger than the ones that you have. I mean, we had natural fractures going up to 100-meter radius, you know, as sort of these circular fractures. And I would think if you hit a inclined, very large feature like that, you definitely would see some interaction in a slick water treatment with a propagating fracture. So it might be interesting just to try just adding, not, you know, just even a few larger, and if you have the capacity to have some inclined features, just match the actual 3D orientation of the sets we found, not just their azimuth.
Mm. Yeah, so the dip would be an interesting one to do. Um, we did try the longer fractures, like 100-meter type length of fracture.
Yeah,
But
but they were
somehow
just like pencil-shaped fractures. They weren't circular fractures.
they were not circular fractures. You're right. So we should make the height also 100 meters and make the length 100 meters is what you're suggesting.
Yeah, just to throw in a couple of those, and 50 meters, you know, a few smaller ones too, just to see what that would do. You don't have to have
Okay.
the full DFN, but just some of these larger features that actually have the full 3D orientation, so dip and azimuth of the fractures that we have found in the core.
Okay. Well, we'll certainly try that. We'll certainly try that.
Yeah, thanks, Alita. Thanks, Nicole. Jonathan McKenna.
Yeah. So thanks for the presentation. That was great. I had a question. I'm interested in the time dependency on the stress shadow effect. When we monitor microseismic events from a surface array, we get focal mechanisms from the rock as it's breaking, and we see that they change from kind of a virgin stress state to this altered stress state due to these stress shadow effects. And then at some time, they go back to a virgin stress state. And I'm wondering if you've looked at this stress shadow time dependency of that stress shadow effect. So if you waited some time for that stress shadow to go away and then pump the subsequent frac, what would that effect be?
That's an interesting observation, Jonathan, because what you would expect is that the stress shadow would be small when the fractures are small, and then it would grow as they grow together and reach a certain size. Once they go beyond that certain size, one fracture primarily propagates upwards, and the other one, maybe the other one propagates towards the side. When that happens, then the stress shadow does become smaller because they're not right next to each other. So you may see, now we haven't looked at that carefully in terms of the magnitude of the stress shadow in each of the elements as a function of time. But I suspect that's what you'll end up seeing, is that you'll end up seeing the stress shadow becoming larger over time. And then in some cases, in some elements, that stress shadow actually going down over time. Now, can you see that in your data? Is that what you're saying?
Yeah, we see the focal mechanisms changing when you kind of refrac an area that's already been treated. So you treat.
We would love to talk to you about it and see what you see. Maybe we can present to us what you've seen, and then see if we can mimic that with our simulations. That would be very interesting.
Yeah, that would be great. I have some papers on that as well. I could direct you to.
Would you please send those to us? We would love to read those and then maybe have a meeting with you.
Yeah, absolutely.
Okay, great. Thank you.
Thanks. Well, I could stay past. I think we actually have this meeting run for another approximately 30 or 35 minutes. So I know some people usually leave at the top of the hour. So in the sake of time, there's a couple of things I wanted to mention while everyone is still here. And the first being that the plans for the next stimulations in 16A are currently underway. You know, what McCool just presented is being part of that overall plan. There's other Forge awardees that have done some stimulation planning. And so the reservoir engineering team led by John McLennan is trying to bring all these recommendations into one coherent stimulation plan that essentially meets as many of the objectives and recommendations as possible. That plan is being reviewed by another panel of industry experts, as well as the STAT and others that have input in how Forge is managed and operated. So the final stimulation, which I believe is going to be happening late this winter, early next spring, somewhere in there. McCool, you may know better than me, but it will try to enfranchise all of the plans and input we've been getting to the degree that it can. So I'm speaking for John there. He couldn't make it today. The other thing, actually, the question I had, and I know there's another question that popped in, but I'm going to take advantage of the time since I'm the host. McCool, are you? So what are your? I have two questions for you. One is just a thought exercise. You know, there have been discussions and talks. You know, we'll essentially do these frac jobs, see where we get potentially hits in 16B, then do a perf job to actually intersect the fractures that come in contact. What are your thoughts on stimulating 16B in areas where some of those fractures come close but don't quite make it? Do you think there's utility in doing, say, a zipper type of operation, or somewhere we can, frac from both sides to enfranchise all those fractures, even ones that maybe I'll call orphaned, in your analysis?
Yeah, that's a really good question. I mean, we assume that any fracture that hits the 16B well is going to get connected to the well. But of course, being cemented and encased and cemented, the term you use, orphaned fracs, is a good one, because you may not be able to connect to the wellbore at all if you don't have any access to the wellbore through the perforations there. So this is something that needs to be discussed as to how we're going to be perforating and stimulating the 16B well, not the A, but the B well.
Mm-hmm. Okay.
And that's something that needs to be thought through. I've raised that question in the past and really haven't had much traction in terms of a discussion, but I think we really do need to discuss that.
Agreed. And just so the other question we got in the chat was, so the models you just presented, you're not losing any fluid to the 16B well. It's considered cased and cemented in your simulations, correct?
That's correct. We're not. Yeah.
My last question is it possible, so if I wanted to take the fracture domains that you just created, is there a way you could export say an XYZ and aperture fields for those created fractures, say in reference to the well or where they were in the well, so that others could take that aperture distribution and do flow and transport simulations with them?
Sure, absolutely. Yeah, I'm happy to do that. I'm sure that's something we can in the format that somebody wants, so we can certainly work on that. One thing I did not mention is that once we create these fractures, we have actually run the heat recovery calculations with the same model, because the same model can actually calculate what kind of heat recovery you get when you start injecting fluid. And so this is something that we have actually run. I didn't show the results today, but we can certainly run some simulations like that and calculate the efficiency of heat recovery for these different designs. And in large part, it's the single biggest thing that affects that, of course, is how many fractures intersect both wellbores. I mean, that controls everything. The branching and the turning and so on is a second order effect compared to that.
Agreed.
So I think this is something that we should absolutely do. And if other people are working on heat recovery and calculations of enthalpy and so on in the geothermal space, then we can certainly make the frac geometry available, and you can use that.
Okay, thank you for that. And I can reach out back to you on that here in the future. I mean, that's something we're working on right now, is trying to better understand the flow testing regime that just happened, in July, and revise some of our conceptual thought of the fractures that have been created, and in anticipation for a new round of thermal recovery and operation optimization type things to help plan flow through experiments that'll happen next year. So that is an active area we're really launching into right now. I know my team is that's our number one priority, then trying to understand some of these next stimulations. So
Yes,
for the next year, that's going to be kind of one of our large chunks of work. So
yeah, absolutely.
okay, are there any further questions while we still have Dr. Sharma? No, silence means that we're finished. So again, let me thank you, Mukul, for your presentation. I really enjoyed it.
Thank you, Rob, and thank you everyone for participating and joining. And if you have any thoughts, please email me, and I'll be happy to respond.
Yeah, this has been recorded. It'll take a few days, but it will show up on the Utah Forge website. And so if you have any, you didn't quite catch something, it'll be there for you to review. And once again, you can reach out to either myself or Professor Sharma, and we'll be happy to entertain a discussion. So I thank everyone for their time today, and we'll see everyone again next month.
Thank you all. Bye.
Bye, everyone. Gosha, can you hear me at all? Are you still on?